In this section, we'll look at how the periodic table is laid out and why elements behave the way they do. This is a piece of sodium. Sodium is a metal. It's a soft metal. It actually could be cut with a knife. And when you put sodium into water, it reacts somewhat violently. And this is gold, also a metal. But when you put gold into water, it doesn't do much of anything. Even though sodium and gold are both metals, they have very different chemical properties. So let's explore why elements behave the way they do. A little chemistry cap for you. We know that the number of protons an atom has tells us what the element is. Copper, for example, atomic number 29, has 29 protons, which is equal to the number of its electrons. Remember that protons have a positive charge and electrons have a negative charge, so atoms then are electrically neutral. And also, because we know those positively charged protons are attracted to the negatively charged electrons, that attraction and the way these electrons are configured determine how that element will react. The fact that positively charged protons and negatively charged electrons are attracted to one another, and that like charges, like these negatively charged electrons, are going to repel one another, is attributed to Coulomb. Coulomb's law states that the strength of the interaction between two electrical charges depends on the sign and the magnitude of those charges and the distance between them. The first part of that accounts for the fact that the oppositely charged particles are attracted to each other, the negatively charged electrons to the positively charged protons. The second part of Coulomb's law is addressing the fact that because these protons are so close to each other, that they're actually going to repel each other with a greater force than these electrons would, which are further apart. Here's the mathematical expression of Coulomb's law. The magnitude of the electrostatic force is equal to a constant, Coulomb's constant, times the product of Q1 and Q2. These represent the magnitude of the charges over the distance between them, squared. Coulomb was a physicist who studied the charges of particles in the late 1700s. His work has since been verified with PES technology, or photoelectric spectroscopy. And it works on the photoelectric effect. So a beam of light that has to be of a high enough energy and a high enough frequency is directed at a surface, and electrons are ejected. And those electrons then are captured and analyzed to determine their charges. And it is this technology that allows us to look at ionization energies. Coulomb's work really allowed scientists to explain why atoms behave the way they do and why elements react the way they do. So we'll take a look next at trends of the periodic table. The first thing we'll take a look at is the trend in size of atoms, or atomic radius. And you can see that as you move from left to right across the period, that the size of the atoms, the radius, decreases. And the reason for this is each time you go across from one element to the next, for example, lithium, starting out with 3 protons and 3 electrons at this size. When you look at beryllium, you're adding a proton. Beryllium has 4 protons and 4 electrons, and an extra neutron or 2 also. And then as you move to boron, you've got 5 protons and 5 electrons, and so forth. 6 protons, 6 electrons, 7 protons, 7 electrons. So each time you add a proton and an electron, you're going to get an increase in the attraction of those particles. And so the size of the atom is going to decrease just a little bit. Each time you add another proton and another electron, those protons and electrons pull each other a little bit more closely. And that is what results in this trend of size decreasing. Now, this is not always going to be exactly like that, but that is what the trend is as you move across the table. You can also see that as you look down a group, atomic radius increases as well. Each time we move down an energy level, we're actually adding another shell for electrons to reside in. And each of those shells is going to be a little bit further and further away from the nucleus. So the size trend as you move down the table, down a group, atomic radius increases. Now we'll take a look at what happens to the size of the atom when it becomes an ion. Here's a sodium atom. It has 11 protons in the nucleus and 11 electrons in its electron cloud. We know we also have some neutrons in the nucleus, but they're not really too important as far as what we're talking about right now. But if you notice the configuration of these electrons, you'll find that there are 2 in the first shell, there are 8 in the second shell, and then there's this 1 valence electron in the third shell. And we know that when sodium ionizes, it gives up that 1 valence electron. And when it gives up 1 valence electron, it still has those same 11 protons in the nucleus. But now that it's lost an electron, it's only got 10 left. And so now we have 11 protons pulling those 10 electrons toward it, and pulling those electrons just a little bit closer toward the nucleus. And so that's why the relative size of a sodium ion is going to be a little bit smaller than that of a sodium atom once it's lost that outer electron. Therefore, metal ions are smaller than their parent atom. Let's look at a nonmetal. Here's a fluorine atom, and it's got atomic number 9, meaning it's got 9 protons in the nucleus and 9 electrons, 2 in the first shell and 7 in its outer shell. And we know that fluorine, in order to become more stable, when it ionizes, it will gain an electron to give it a full valence of 8. And so once fluorine has gained that additional electron to give it a valence of 8, in addition to the 2 in its inner shell, it now has 10 electrons and 9 protons. So by adding an extra electron to that atom, we're increasing now the number of repulsions in that electron cloud. And so the fluoride ion is going to be a little bit larger than its parent atom because of the additional repulsions of that extra electron. And so ions of nonmetals, or anions, tend to be slightly larger than their parent atom. Next, we'll take a look at ionization energy, which is the energy required to remove an electron from a ground state atom. Let's take a look at a lithium atom. Lithium's electron configuration is 1s2, 2s1. We have 2 electrons in the first shell, or the 1s orbital, and 1 electron in the second shell, in the 2s orbital. And we know that lithium will become a lot more stable if it can get rid of that 1 electron, giving it a full valence of 2 in its core. And since lithium will give that 1 valence electron up fairly easily, taking very little energy, lithium then has a fairly low ionization energy. If we take a look at beryllium, we see that beryllium's electron configuration is 1s2, 2s2. And so beryllium's 4 electrons, 2 of them are residing in the 1s orbital, closest to the nucleus, and the other 2 reside in the 2s orbital in the second shell. And remember that those s orbitals only hold 2 electrons apiece. There's only 1 s orbital in a given sublevel. So these are 2 pretty stable orbitals. And so if I want to try to remove an electron from an orbital that is full, it's going to take a little bit more energy. So beryllium's ionization energy is going to be a bit higher than lithium's. Move down the second period to fluorine. So fluorine, atomic number 9, then has 9 protons in the nucleus and 9 electrons. So we have 2 in the first shell, and we have 7 in the second shell. And we know that fluorine, being a nonmetal, would like to gain an electron to give it a complete valence of 8 in its outer shell. And so if chlorine wants to gain an electron, and we want to try to remove an electron, it's going to take a lot of energy to remove one of fluorine's electrons. All of these electrons in the valence are approximately the same distance from the nucleus. And so those protons in the nucleus have a good attraction for its electrons in the valence. And so the trend for ionization energy as you move across a period on the periodic table is that ionization energy will increase as you move from left to right. Now we'll take a look at the ionization energy of a sodium atom. Again, sodium is a metal. It has now 2 electrons in its 1s orbital, and then it has 8 electrons in its second shell, its 2s and its 2p, and then in the third shell it has this 1 valence electron. And so once again, since we have an orbital that has only 1 electron in it, sodium will give that up rather easily. In fact, even more easily than lithium gave up its 1 valence electron. And the reason for that is shielding. Protons in the nucleus of the atom are attracted to the electrons in the atom's core, or the inner electrons in the inner shells. And these inner shell core electrons shield the valence electrons from the pull of the nucleus, making it a little bit easier to remove that valence electron. So these inner electrons are called the core electrons, and they are in effect shielding or insulating the valence electron from the pull coming from the protons in the nucleus. And so, as you move down a group in the periodic table, ionization energies tend to decrease, making it easier to remove the valence electron from a really big atom down here. And because francium is such a large atom with 87 protons and 87 electrons, it's got 6 layers of core electrons that are shielding the pull from the nucleus, making its valence electron, which is located in the 7th shell, relatively easy to remove. It's so far away from the pull of the protons in the nucleus. And that's one of the reasons that francium is so reactive. That 1 valence electron comes up pretty easily. So let's take a look at ionization energies and comparing different elements to each other. And so you can see here we have ionization energies on the y-axis, and we have the atomic numbers on the x-axis. So if we start with our first, let's start actually here with hydrogen. And so our atom of hydrogen has 1 proton and 1 electron. And you can see where its ionization energy lies. Now, it's kind of up there a little bit compared to some of the elements that are down here. And that's because even though it only has 1 valence electron, it's got 1 proton, and they're very close to each other. It's a very small atom. So Coulomb's law says that the attraction is going to be pretty great between those two just because the distance isn't very far. But hydrogen does ionize fairly easily and will give up that 1 valence electron that it has. Now we'll compare that ionization energy of hydrogen to helium. And here's an atom of helium, 2 protons, a couple of neutrons, and 2 electrons. So why is helium's ionization energy so high? Well, first of all helium has is a 1s orbital, and it's got 2 electrons in it, and that orbital can only hold 2 electrons. So it's got a full valence with those 2 electrons. And size-wise, since there's only one shell in a helium atom, the electron is really pretty close to the nucleus here, again, because Coulomb's law says so. And so that's a pretty strong attraction. So helium, because it has a full valence, is very, very stable and does not want to change its electron configuration. So therefore, the ionization energy, trying to get an electron off of a helium atom, is going to be really, really difficult. It's going to really require a lot of energy. And now we'll take a look at lithium. Lithium's ionization energy is really low compared to hydrogen even. And both hydrogen and lithium have just 1 valence electron. So what's the difference? Well, a lithium, first of all, atom has 3 protons and 4 neutrons in the nucleus. And it also has 3 electrons. So the first 2 electrons are in that first shell, in the s orbital. And so that is a full inner 1s orbital. And then that third electron is hanging out here in the second shell all by itself. And so the one electron that is most easily going to be removed from the lithium atom, first of all, is a little bit further away, because lithium actually has 2 shells instead of the 1 that hydrogen has. And these 2 electrons that are in here, called the core, everything that's inside of the valence is known as the core electrons, are shielding some of the attraction of the positive charge in the nucleus. And we'll talk about shielding again in just a little bit. But it's not going to take a whole lot of energy to remove lithium's outer valence electron, because, first of all, it's not in a full orbital. There's still room for 1 more electron in there, so it's not a particularly stable orbital. And second of all, that valence electron is pretty far away from the nucleus compared to hydrogen, which is a much smaller atom. And here's neon, another noble gas, and it's got 8 electrons in its valence, which means it has a full valence, and so it's an extremely stable atom, and it's not going to want to give up an electron. And so the ionization energy for neon is going to be really pretty high, because it's not going to, it's going to be very difficult to remove an electron, first of all, from a full valence. And so you can see, as you move across a period, the general trend is for ionization to increase as you move from left to right across the table. But every now and again, you can see there are a couple of little blips here where elements don't exactly follow that trend. So let's take a look at why something like that might happen. So take a look at nitrogen's electron configuration, and we'll compare that to oxygen. So nitrogen is a 1s2, 2s2, 2p3. And so we have 1 electron in the X, 1 in the Y, and 1 in the Z. So we have 3 orbitals here that each have 1 electron in them. So these 3 electrons are going to kind of space themselves pretty far apart because they're all in separate orbitals. Then when we move to oxygen, we've now got a 1s2, a 2s2, a 2p4. So we have 2 electrons in the X orbital, shown in this box diagram, and 1 in the Y and 1 in the Z. Okay, now take a look here. Nitrogen's ionization energy is a little bit higher than oxygen, so it's going to require a little bit more energy to remove one of these. Why? Well, let's take a look again at oxygen. So here, the difference between oxygen and nitrogen is this 1 electron that's sitting in this p orbital. Well, what happens when you have when you have 2 electrons in 1 orbital, you're going to get an additional repulsion. Now, remember, these 3 were all pretty far apart. But having this additional electron right here occupying that p orbital and increasing the repulsions that are going on in that p orbital are going to make it a little bit easier to pull one of those electrons off of oxygen. So that's why oxygen is going to have a lower ionization energy than nitrogen would. The last trend that we'll take a look at is electron affinity. And electron affinity is the energy change that happens when an electron gets added to an atom. And while ionization energy is always a positive value because we're talking about removing an electron from an atom and that requires energy, in most instances, energy is going to be released when an electron is added. Remember our fluorine atom. It has 7 electrons in its valence. And so when it gains that 8th electron, fluorine is going to give off energy. And so the value of electron affinity will be a negative value. Ionization energy looks at how easy it is for an atom to lose an electron, whereas electron affinity looks at how easily an atom will gain an electron. And so to review the trends of the periodic table, first we looked at the size of the atom, the radius of the atom, and we saw that the trend typically is that atomic radius will decrease as you move across a period and increase as you go down a group. We looked at ionization energy as well, and ionization energy increases as you go across a period and decreases as you move down the group. And then finally we looked at electron affinity, which increases as you move across a period and decreases as you move down a group. And remember that these are trends, and so they don't always follow the exact pattern that you would expect, but they are trends. And so I hope this has helped you to understand how an atom's electron configuration helps to determine the chemical properties of the element.